Tonight, we embark on one of the most profound journeys in modern physics. We are going to explore a theory that fundamentally challenges everything you thought you knew about the nature of space and time. We are going to discover loop quantum gravity, a revolutionary approach to understanding the universe at its most fundamental level. By the end of this exploration, you will understand why some of the world's leading physicists believe that space itself might be made of tiny, indivisible pieces woven together like threads in an impossibly fine fabric. Before we begin, if you find these deep explorations of physics and the cosmos meaningful, please consider subscribing to the channel. Your support helps bring these journeys into the unknown to more curious minds. Now, settle in, relax, and let us venture into the quantum realm of space and time itself. The great divide in physics. To understand why loop quantum gravity exists, we must first appreciate one of the most profound puzzles in all of physics. It is a puzzle that has haunted scientists for nearly a century. On one side, we have Albert Einstein's masterpiece, the general theory of relativity. On the other side, we have the extraordinary framework of quantum mechanics. Both theories are spectacularly successful. Both have been tested to incredible precision, and yet both fundamentally contradict each other in ways that seem impossible to reconcile. General relativity, published by Einstein in 1915, describes gravity not as a force in the traditional sense, but as the curvature of space and time. Massive objects like stars and planets bend the fabric of space-time around them, and other objects follow the curves in this fabric. It is an elegant geometric picture. The mathematics of Riemannian geometry, developed by Bernhard Riemann in the 19th century, provides the tools to describe how space-time curves and warps. In this picture, space-time is smooth and continuous. You can divide any region of space into smaller and smaller pieces without limit. There is no smallest unit, no fundamental grain to the fabric of existence. Space-time flows like water, infinitely divisible. This theory has been tested countless times. It correctly predicted the bending of starlight around the sun, first confirmed during a solar eclipse in 1919. It predicted the existence of black holes, those regions where space-time curves so severely that nothing, not even light, can escape. It predicted gravitational waves, ripples in the fabric of space-time itself, which were finally detected directly by the LIGO observatories in 2015. Almost exactly 1 century after Einstein wrote down his equations, general relativity describes the large-scale structure of the universe with breathtaking accuracy. Quantum mechanics, developed in the 1920s through the work of Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and many others, describes the behavior of matter and energy at the smallest scales. It tells us that at the atomic and subatomic level, the world is fundamentally different from our everyday experience. Particles do not have definite positions until they are measured. Energy comes in discrete packets called quanta. There is inherent randomness built into the fabric of reality. The Heisenberg uncertainty principle tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely we measure one, the less precisely we can know the other. Quantum mechanics has been tested even more rigorously than general relativity. It correctly predicts the behavior of atoms, the emission spectra of elements, the properties of semiconductors that power our computers and phones. the interactions of subatomic particles in accelerators like the Large Hadron Collider, the quantum theory of electromagnetic interactions, known as quantum electrodynamics, agrees with experiment to more than 10 decimal places. It is the most precisely tested theory in all of science. Here is the problem. General relativity treats spacetime as a smooth, continuous backdrop against which physics plays out. Quantum mechanics treats space and time as a fixed stage on which particles dance and interact. But quantum mechanics also tells us that everything is subject to quantum uncertainty. If spacetime itself is a physical entity, as general relativity claims, then spacetime itself should be subject to quantum effects. At small enough scales, spacetime should fluctuate and foam, should exhibit the same fuzzy probabilistic behavior that electrons and photons display. But when physicists try to apply the standard techniques of quantum mechanics to the gravitational field, they encounter a disaster. The calculations produce infinities. The theory becomes mathematically inconsistent. The tried and tested methods that worked so beautifully for electromagnetism and the nuclear forces fail completely when applied to gravity. This failure is not a minor technical difficulty. It represents a fundamental incompatibility between our two best theories of how the universe works. This incompatibility becomes most severe in two situations. The first is at the center of black holes, where general relativity predicts that matter collapses to a point of infinite density called a singularity. The second is at the very beginning of the universe, at the moment of the Big Bang, where all matter and energy were compressed into an infinitely small, infinitely dense point. At these singularities, the smooth spacetime of general relativity breaks down completely. The equations give nonsensical answers. Densities become infinite, curvatures become infinite. Physics, as we know it, ceases to make sense. These singularities are not just mathematical curiosities. They represent real physical situations where we genuinely do not know what happens. What is actually at the center of a black hole? What really happened at the instant of the Big Bang? Our current theories cannot answer these questions. To answer them, we need a quantum theory of gravity, a theory that combines the insights of general relativity with the framework of quantum mechanics. We need to understand what happens to spacetime itself when quantum effects become important. This is the quest for quantum gravity, and it has occupied some of the greatest minds in physics for decades. Several approaches have been developed. String theory proposes that fundamental particles are actually tiny vibrating strings, and that spacetime has extra hidden dimensions beyond the three of space and one of time that we experience. Causal dynamical triangulations attempt to build spacetime from small building blocks that must be assembled according to certain rules. Asymptotically safe gravity proposes that gravity becomes well-behaved at high energies through a mechanism called asymptotic safety. And then there is loop quantum gravity, the subject of our exploration tonight. Loop quantum gravity takes a different approach than its competitors. Rather than adding new ingredients like extra dimensions or fundamental strings, it takes the core insights of general relativity seriously and applies the methods of quantum mechanics directly to spacetime itself. The result is a radical new picture of reality, one where space is not infinitely divisible, but is made of discrete, quantized pieces, where there is a smallest possible length and a smallest possible volume. where the smooth fabric of spacetime, described by Einstein, emerges from a deeper, grainier quantum reality. This is the story we will explore together. It is a story of brilliant physicists grappling with the deepest questions about the nature of reality. It is a story of mathematical beauty and conceptual revolution. And it is a story that may ultimately tell us what space and time truly are at the most fundamental level. The Planck scale, the edge of known physics. To understand loop quantum gravity, we must first journey to a scale so small that it challenges the very limits of imagination. This is the Planck scale, named after the German physicist Max Planck, who first calculated these fundamental units in 1899. The Planck scale represents the boundary where our current understanding of physics breaks down, where the smooth space-time of Einstein gives way to something stranger and more fundamental. The Planck length is approximately 1.6 times 10 to the negative 35 meters. Let us try to grasp just how small this is. An atom is about 10 to the negative 10 meters across. The Planck length is smaller than an atom by roughly the same factor that an atom is smaller than the entire observable universe. If you were to enlarge an atom to the size of the observable universe, the Planck length would still be smaller than a typical atom in that enlarged picture. It is almost impossibly small, far beyond anything we can directly probe with current or foreseeable technology. To put it another way, the smallest length scales we have ever experimentally probed are around 10 to the negative 18 meters, achieved at particle accelerators like the Large Hadron Collider. The Planck length is 17 orders of magnitude smaller than this. We are as far from the Planck scale as the Large Hadron Collider is from the size of a galaxy. The gulf is enormous. Accompanying the Planck length is the Planck time, approximately 5.4 times 10 to the negative 44 seconds. This is the time it takes light, the fastest thing in the universe, to travel one Planck length. Just as the Planck length is unimaginably small, the Planck time is unimaginably brief. In the time it takes you to blink, roughly 300 milliseconds, light could traverse a distance of about 90,000 kilometers. In one Planck time, light travels the Planck length, a distance so small it defies comprehension. There is also the Planck mass, about 2.2 times 10 to the negative 8 kilograms, roughly the mass of a small grain of sand. This might seem unremarkable until you realize that this mass, concentrated into a region the size of the Planck length, would create a black hole. The Planck energy related to the Planck mass through Einstein's famous equation relating energy and mass is about 1.2 times 10 to the 19 giga-electron volts. This is roughly 100 trillion times the energy achieved by the Large Hadron Collider. It is the energy scale at which quantum gravitational effects become unavoidable. These Planck units are not arbitrary choices. They are constructed from the three fundamental constants that govern quantum mechanics, relativity, and gravity. The speed of light, roughly 300,000 kilometers per second, tells us how fast information can travel and connects space and time in special relativity. The reduced Planck constant, about 1.5 times 10 to the negative 34 joule seconds, quantifies the fundamental graininess of quantum mechanics. And Newton's gravitational constant, about 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared, determines the strength of the gravitational force. When you combine these three constants in the right way, you get the Planck units. There is no other choice. The Planck length, time, mass, and energy are the unique scales where quantum mechanics, relativity, and gravity all become important simultaneously. They mark the frontier where our established theories break down, and something new must take over. What happens at the Planck scale? The honest answer is that we do not know for certain, but we can make educated guesses based on combining quantum mechanics and general relativity. The Heisenberg uncertainty principle tells us that if we try to measure a position very precisely, there is inherent uncertainty in the momentum, and vice versa. Following this reasoning, if we try to confine something to a region smaller than the Planck length, the uncertainty in its energy becomes so large that the energy density could exceed the threshold for creating a black hole. This implies that attempting to probe distances smaller than the Planck length may cause the very fabric of spacetime to tear itself apart, collapsing into quantum black holes. Based on this analysis, we can infer that the Planck length may represent a genuine physical limit, not just an arbitrary unit. There may be no such thing as a distance smaller than the Planck length. The concept of length itself may cease to have meaning below this scale. Similarly, there may be no duration shorter than the Planck time. Time itself may tick forward in discrete steps, like a digital clock with unimaginably high precision, rather than flowing continuously as we normally imagine. This idea that space and time might be discrete rather than continuous at the Planck scale is one of the central predictions of loop quantum gravity. The theory suggests that just as matter is made of atoms and light is made of photons, space and time may be made of discrete quanta. Just as you cannot have half an electron or a third of a photon, this would mean you cannot have a region of space smaller than a certain minimum size, or a duration shorter than a certain minimum time. If correct, this represents one of the most profound revisions to our understanding of physical reality. The physicist John Wheeler, one of the pioneers of quantum gravity, coined the term quantum foam to describe what space-time might look like at the Planck scale. Imagine looking at the surface of the ocean from space. It appears smooth and calm, but as you descend closer and closer, you see waves, then ripples, then the churning turbulence of water molecules bouncing off each other. Wheeler proposed that spacetime undergoes a similar transformation as you zoom in to the Planck scale. What appears smooth and continuous from far away becomes a roiling, fluctuating foam of quantum geometry at the smallest scales. In this picture, spacetime at the Planck scale is nothing like the placid four-dimensional continuum of general relativity. It is a dynamic, ever-changing froth, where the very concepts of distance and duration become fuzzy and uncertain. Virtual black holes flash in and out of existence. The topology of space, the way different regions are connected to each other, fluctuates wildly. The neat distinction between space and time breaks down. This is the quantum gravitational regime, and it is here that loop quantum gravity makes its home. The remarkable thing about loop quantum gravity is that it provides a precise mathematical description of this quantum foam. It gives us tools to calculate what space-time looks like at the Planck scale, what properties it has, how it evolves. The foam is not just a vague metaphor, but a concrete mathematical structure, and that structure turns out to have surprising and beautiful properties. The birth of loop quantum gravity. The story of loop Quantum gravity begins in the mid-20th century with the first serious attempts to quantize gravity. The Wheeler-DeWitt equation, developed by Bryce DeWitt and John Archibald Wheeler in the 1960s, represented one of the earliest attempts to write down a quantum theory of gravity. Wheeler, who also gave black holes their evocative name and championed the idea of quantum foam, worked with DeWitt to formulate what they hoped would be the fundamental equation governing the quantum universe. The Wheeler-DeWitt equation has a startling property. Unlike the Schrödinger equation of ordinary quantum mechanics, which describes how a quantum state evolves in time, the Wheeler-DeWitt equation has no time variable at all. It is, in a sense, timeless. The equation simply states that a certain operator, the Hamiltonian constraint, annihilates the wave function of the universe. This leads to what is known as the problem of time in quantum gravity. If the fundamental equation of the universe contains no time, where does our experience of time come from? How does anything happen? This profound conceptual puzzle remains at the heart of quantum gravity research to this day. For decades, the Wheeler-DeWitt equation remained largely formal. It was elegant but seemed nearly impossible to solve. The space of all possible three-dimensional geometries, called superspace, is infinite dimensional and poorly understood. The equation was written down, but physicists had little idea how to extract concrete predictions from it. The breakthrough came in 1986 when Abhay Ashtekar, a physicist at Pennsylvania State University, discovered a new way to write down general relativity. Instead of using the metric, which describes distances and angles in spacetime, Ashtekar reformulated gravity in terms of connections and triads. A connection describes how to parallel transport objects along curves in spacetime, essentially how to compare directions at different points. A triad is a kind of frame field that specifies what directions count as up-down, left-right, and forward-backward at each point. This reformulation might seem like a mere mathematical curiosity, a different way of writing down the same physics, but it turned out to be profoundly important. Ashtekar's new variables made the structure of general relativity look remarkably similar to Yang-Mills theory, the framework that describes the strong and weak nuclear forces in particle physics. Yang-Mills theory had been successfully quantized using techniques developed by physicists like Kenneth Wilson, who introduced the concept of Wilson loops to describe gauge fields. With gravity now resembling a Yang-Mills theory, perhaps the same techniques could be applied. Shortly after Ashtekar's reformulation, Ted Jacobson and Lee Smolin realized something remarkable. When they wrote the Wheeler-DeWitt equation using Ashtekar's new variables, they found that certain special states described by loops, were exact solutions of the equation. These loop solutions were not approximate or perturbative. They solved the quantum gravity equations exactly. For the first time, physicists had found honest-to-goodness solutions to the quantum gravity equations. This discovery sparked intense excitement. Carlo Rovelli, then a young physicist at the University of Pittsburgh, joined forces with Lee Smolin to develop these ideas further. Together they worked out the mathematical structure of what they called the loop representation of quantum gravity. In this representation, the fundamental quantum states of spacetime are described not by smooth fields spread throughout space, but by networks of loops, one-dimensional structures carrying quantum numbers. In their work between 1988 and 1990, Rovelli and Smolin showed that the loop representation provided a rigorous mathematical framework for quantum gravity. The loops were not arbitrary mathematical constructs, but had a concrete physical interpretation. They represented the fundamental excitations of the gravitational field, analogous to how photons are the fundamental excitations of the electromagnetic field. But whereas photons travel through space, the loops of quantum gravity are space. They are the quantum threads from which the fabric of the universe is woven. The development continued rapidly. Jorge Pulin and Jerzy Lewandowski recognized that the intersections of loops, not just the loops themselves, played a crucial role in the theory. When loops intersect, they create vertices, and these vertices carry their own quantum numbers. The theory should be formulated not just in terms of isolated loops, but in terms of graphs, networks of links and nodes where loops can branch and reconnect. The decisive step came in 1994 and 1995, when Rovelli and Smolin showed that the quantum operators corresponding to area and volume have discrete spectra. This was a stunning result. In classical general relativity, areas and volumes can take any values whatsoever. A surface can have an area of 1 square meter, or 1001 square meters, or any other value you can imagine. The areas form a continuous spectrum. But in the quantum theory, Rovelli and Smolin demonstrated that areas and volumes are quantized. Just as the energy levels of a hydrogen atom come in discrete steps, so too do the areas and volumes of quantum spacetime. This quantization of geometry is perhaps the central result of loop quantum gravity. It tells us that space is not infinitely divisible. There is a smallest possible area, roughly the Planck area, about 10 to the negative 70 square meters. There is a smallest possible volume, roughly the Planck volume, about 10 to the negative 105 cubic meters. Below these scales, the concepts of area and volume simply do not exist. Spacetime is grainy, atomic, made of discrete pieces rather than continuous fluid. The mathematical structures that label these discrete quantum states turned out to be closely related to objects called spin networks, which had been invented decades earlier by the mathematician Roger Penrose in a completely different context. Penrose had proposed spin networks as a purely combinatorial way to build up angular momentum from more fundamental building blocks. He had no idea that his abstract mathematical constructions would turn out to describe the quantum structure of spacetime itself. A spin network is a graph, a collection of nodes connected by links. Each link carries a label called a spin, which is a half integer like 1/2, 1, 3/2, 2, and so on. Each node carries an additional label called an intertwiner, which describes how the spins at that node combine with each other. These labels are not arbitrary decorations, but encode the quantum geometry of space. The spins determine the areas of surfaces that cross the links, while the intertwiners determine the volumes of regions surrounding the nodes. Imagine a vast network of threads, each thread labeled with a spin. Where threads meet, there are nodes with additional labels. This network is space itself. The threads are not objects existing within space. They are the atoms from which space is constructed. The three-dimensional geometry we experience emerges from this underlying discrete structure in the same way that the smoothness of water emerges from the underlying discreteness of water molecules. Thomas Thiemann, working in the late 1990s, made crucial contributions to establishing the mathematical consistency of the theory. He showed how to define the Hamiltonian constraint, the quantum analog of the Wheeler-DeWitt equation, as a well-defined operator acting on spin network states. This work was essential for establishing that loop quantum gravity is a mathematically coherent theory, not just a collection of suggestive ideas. Over the following decades, research in loop quantum gravity unexpanded enormously. The covariant formulation known as spin foam theory was developed by Rovelli, Michael Reisenberger, John Barrett, Louis Crane, Laurent Friedel, Kirill Krasnov, Roberto Pereira, Jonathan Ingle, and many others. Applications to cosmology and black hole physics were explored. New mathematical techniques were developed. Today, loop quantum gravity represents one of the most active and vibrant research programs in theoretical physics, with approximately 30 research groups worldwide contributing to its development. Background independence, the radical foundation. One of the most important features of loop quantum gravity, and one that sets it apart from many other approaches to quantum gravity, is its background independence. This technical-sounding term refers to a profound conceptual principle that lies at the heart of general relativity, and loop quantum gravity proponents argue must be preserved in any quantum theory of gravity. In ordinary physics, we typically describe phenomena by specifying where and when they occur. An electron is at position x at time t. A wave passes through location y at time s. Space and time form a fixed stage, a backdrop against which the drama of physics unfolds. The actors, the particles and fields, move around on this stage, but the stage itself remains fixed and unchanging. This is what physicists call a background spacetime. This background dependence works perfectly well for most of physics. When we study electromagnetism or the nuclear forces, we can imagine spacetime as a pre-existing arena in which electric and magnetic fields propagate, in which particles interact. The spacetime provides a reference frame for describing where things are and when things happen, but general relativity changes everything. In Einstein's theory, spacetime is not a passive backdrop. It is a dynamical entity in its own right. The gravitational field is spacetime. When we talk about the curvature of spacetime caused by a massive object, we are not talking about something happening within spacetime. We are talking about spacetime itself changing, warping, evolving. The stage has become one of the actors. This means that the notion of position and time as fixed reference points breaks down. In general relativity, there is no absolute meaning to the statement that an event occurs at position x and time t. Coordinates are just labels, convenient bookkeeping devices that have no intrinsic physical significance. What matters are the relationships between events, the distances and durations measured by physical clocks and rulers, not some abstract coordinate system imposed from outside. This relational character of spacetime is called diffeomorphism invariance, or general covariance. A diffeomorphism is a smooth transformation that relabels points in spacetime. General relativity says that such relabeling cannot have any physical consequences. If I call a point X and you call it Y, we should predict exactly the same physics. The physical content of the theory lies entirely in the relationships between events, not in the names we give them. Now here is the crucial question: what happens when we try to quantize gravity? In standard quantum field theory, we quantize fields that propagate on a background spacetime. The electromagnetic field is spread out over space and time. We treat the positions and times as fixed reference points and calculate how the field fluctuates and interacts with charged particles. This procedure gives us quantum electrodynamics, the remarkably successful quantum theory of light and electrons. But if we try to apply this procedure directly to gravity, we run into a contradiction. Gravity is spacetime. If we treat spacetime as a fixed background on which the gravitational field propagates, we are treating gravity differently from how general relativity tells us to treat it. We are putting the background back in, even though Einstein taught us that there is no background. We are smuggling in absolute structure that the theory itself says does not exist. This is the problem that background independence addresses. A background-independent quantum theory of gravity does not assume the existence of any fixed spacetime. It does not quantize fields living on a pre-existing stage. Instead, it quantizes spacetime itself. Space and time emerge from the quantum theory, rather than being assumed from the outset. Loop quantum gravity is designed from the ground up to be background independent. When we define spin networks and spin foams, we do not place them within some pre-existing spacetime. The spin networks are spacetime. The nodes and links of the network define what space is, not the other way around. There is no ambient space in which the spin networks float. There are just the spin networks themselves and the quantum relationships between them. This might seem strange or even paradoxical. How can we do physics without space and time? How can we talk about what happens if there is no background time in which events occur? These are deep questions that loop quantum gravity forces us to confront. The answer lies in thinking relationally. Instead of asking where something is or when something happens in absolute terms, we ask how things are related to each other. Instead of placing events on a pre-existing timeline, we look at which events are before which other events, what the durations are between them as measured by physical clocks. The physics is entirely contained in these relationships. This relational approach has profound implications. It means that the smooth, continuous spacetime of our everyday experience is not fundamental. It is emergent. At the Planck scale, there is no smooth spacetime, just a discrete network of quantum relationships. The spacetime we experience emerges from this underlying quantum structure in a limit, like how the smoothness of a piece of fabric emerges from an underlying weave of individual threads. Carlo Rovelli, one of the founders of loop quantum gravity, has been particularly eloquent about the philosophical implications of background independence. He argues that we must let go of the idea that the world inhabits space and evolves in time. Instead, space-time itself is dynamical, constructed from the quanta of the gravitational field. What we call space is just a particular way of describing the quantum state of these gravitational quanta at a given instant. What we call time is just a label for how these quantum states are related to each other. Critics of loop quantum gravity sometimes argue that background independence is too radical, that it makes the theory too difficult to work with. String theory, the main competitor to loop quantum gravity, is typically formulated on a fixed background spacetime. Strings propagate through a pre-existing 10-dimensional space. The background provides a convenient framework for calculations, but proponents of loop quantum gravity counter that background. Independence is not optional. It is a requirement dictated by general relativity itself. Einstein's great insight was that spacetime is dynamical, that there is no absolute background. Any quantum theory of gravity that respects this insight must be background independent. To do otherwise is to throw away the central lesson that general relativity taught us. The debate continues, and both approaches have made significant progress. But background independence remains one of the defining features of loop quantum gravity, one that shapes everything from its mathematical formulation to its physical predictions. Spin networks, the atoms of space. We have arrived at the heart of loop quantum gravity, the mathematical structure that describes the quantum nature of space at the smallest scales. These are the spin networks, and they represent one of the most beautiful and surprising discoveries in modern theoretical physics. Just as the periodic table reveals the atomic structure underlying the diversity of chemical elements, spin networks reveal the discrete structure underlying the continuity of space itself. A spin network is a graph, a collection of nodes connected by links. Imagine a three-dimensional web of connections, somewhat like a network of roads connecting cities, or the bonds connecting atoms in a molecule. But a spin network is not embedded in some pre-existing space. The spin network is space. The nodes and links define what geometry is, rather than being placed within a geometry that already exists. Each link in a spin network carries a label called a spin. In physics, spin is a fundamentally quantum property related to angular momentum. The spins on the links of a spin network are half integers: 1/2, 1, 3/2, 2, 5/2, and so on. These spins are not arbitrary decorations. They have profound physical significance. The spin on a link determines the quantum of area associated with any surface that crosses that link. The formula for the area eigenvalues is one of the most important results in loop quantum gravity. If a surface is crossed by a link carrying spin j, that link contributes to the total area an amount proportional to the square root of j times j plus 1, multiplied by a fundamental constant that includes the Planck area and a parameter called the Emirzi parameter. For a spin of 1/2, the contribution is proportional to the square root of 3 divided by 4. For a spin of 1, it is proportional to the square root of 2, and so on for higher spins. The total area of a surface is found by summing up the contributions from all the links that cross it. Since each link contributes a discrete amount, the total area must also be discrete. There is a smallest possible non-zero area, corresponding to a surface crossed by a single link of the minimum spin. This minimum area is roughly the Planck area, about 10 to the negative 70 square meters. Any surface in the universe has an area that is a multiple of this fundamental unit. Now let us consider the nodes of the spin network. Nodes are points where links meet. At a node, several links come together, and their spins must combine according to the rules of quantum angular momentum. Just as the spins of two electrons can add together to give a total spin of 0 or 1, the spins at the nodes of a spin network can combine in various ways, labeled by mathematical objects called intertwiners. The nodes carry physical information about volume, whereas the links encode the areas of surfaces. The nodes encode the volumes of regions. A region of space containing several nodes has a total volume that depends on the intertwiners at those nodes. Like area, volume is also quantized. There is a smallest possible non-zero volume, roughly the Planck volume, about 10 to the negative 105 cubic meters. The spectrum of volume eigenvalues is more complicated than that of area. The area spectrum is relatively simple, given by the formula involving the square root of j times j plus 1. The volume spectrum is richer and has been computed explicitly only in certain cases, but the key point remains. Volumes, like areas, come in discrete steps. Space is granular. What does a spin network actually look like? Imagine an enormously complicated three-dimensional graph with countless nodes and links stretching in all directions. The graph has no particular shape or structure imposed from outside. There is no ambient space in which to draw it. The graph just exists as an abstract mathematical object with nodes, links, spins, and intertwiners. Now imagine zooming out, looking at this graph from farther and farther away. At some point, the discrete structure becomes invisible, and what you see instead is a smooth, three-dimensional space. The countless tiny chunks of area and volume blend together into what appears to be a continuous fabric. This is the familiar, three-dimensional space of everyday experience, the space in which we move around and live our lives. But at the fundamental level, it is all made of spin networks. Roger Penrose invented the idea of spin networks in the early 1970s, long before loop quantum gravity existed. Penrose was interested in the foundations of quantum mechanics, particularly the question of where space comes from. He proposed that the basic building blocks of geometry should be purely combinatorial, based on discrete mathematical structures rather than continuous manifolds. His spin networks were designed to satisfy this requirement. Penrose's idea was largely forgotten until it was rediscovered by the loop quantum gravity community in the 1990s. When Rovelli and Smolin were developing the loop representation of quantum gravity, they found that their quantum states of geometry were naturally labeled by spin networks. Penrose's abstract mathematical constructions turned out to describe the actual quantum structure of physical space. It was a remarkable convergence of independent lines of thought. The spin networks of loop quantum gravity are not quite the same as Penrose's original version. Penrose's spin networks were designed to describe angular momentum and were not explicitly related to spacetime. The loop quantum gravity version incorporates the connection between spin networks and geometry, making the physical interpretation explicit. But the mathematical structure is closely related, and Penrose's original insight proved prophetic. Let us try to visualize what this means for our understanding of space. Take a cubic meter of empty space far from any matter. In classical general relativity, this cubic meter is perfectly smooth and continuous. You can divide it into smaller and smaller cubes without limit. But in loop quantum gravity, this cubic meter is actually a quantum superposition of countless spin network states. Each spin network represents a possible discrete geometry for that region of space. If we somehow measured the volume of that cubic meter with perfect precision, we would not get exactly 1 cubic meter. We would get one of the discrete eigenvalues of the volume operator, close to, but not exactly equal to 1 cubic meter. The difference would be incredibly tiny, far below any current measurement capability. But in principle, the discrete nature of space would reveal itself. Similarly, if we measured the area of one face of that cube with perfect precision, we would get a discrete value, one of the eigenvalues of the area operator. The areas and volumes of any region of space are fundamentally quantized, taking only certain allowed values from a discrete spectrum. This picture has profound implications. It suggests that the infinity problems that plague traditional approaches to quantum gravity might be resolved. When we try to quantize gravity using ordinary methods, we encounter infinities because we integrate over arbitrarily small distances and arbitrarily high energies. But if space itself has a minimum size, these integrations are automatically cut off. There is a natural smallest scale, and physics below that scale simply does not exist. The spin network picture also provides a new perspective on the nature of space itself. Space is not a thing, a substance that fills the universe. Space is a relationship, a pattern of connections between discrete quanta of geometry. The nodes of a spin network are the fundamental atoms of space. The links connecting them describe how those atoms are related to each other. The smooth continuum of everyday space emerges from these relationships in a coarse-grained limit, just as the smooth flow of water emerges from the discrete interactions of water molecules. Spin foams, how quantum space evolves. Spin networks describe the quantum geometry of space at a single instant. But the universe is not static. It evolves, changes, develops over time. To have a complete theory of quantum gravity, we need to understand not just what space looks like at a given moment, but how it changes from one moment to the next. This is where spin foams enter the picture. A spin foam is to space-time what a spin network is to space. If we imagine a spin network as a snapshot of quantum geometry at one instant, then a spin foam is a movie of quantum geometry, showing how the spin network changes over time. The nodes of the spin network trace out lines as time passes. The links trace out surfaces. And the spin foam is the collection of all these lines and surfaces, together with the labels they carry. More precisely, a spin foam is a two-dimensional cell complex. Where a spin network has nodes and links, a spin foam has vertices, edges, and faces. The faces are two-dimensional surfaces, labeled by spins, just as the links of a spin network carry spins. The edges are one-dimensional lines where faces meet, carrying additional labels. And the vertices are points where edges meet, representing moments when the topology of space changes. The relationship between spin networks and spin foams is analogous to the relationship between particles and their world lines in ordinary physics. A particle moving through space traces out a curve, a world line in space-time. The particle at any instant is a point, but over time, it sweeps out a one-dimensional history. Similarly, a spin network at any instant is a graph, but over time, it sweeps out a two-dimensional structure, a spin foam. At the boundary of a spin foam, you find spin networks. If you take a slice through a spin foam at a particular instant, you get a spin network representing space at that instant. Different slices give different spin networks. The spin foam interpolates between these spatial geometries, describing how they transform into each other. This covariant formulation of loop quantum gravity, describing space-time rather than just space, was developed in the late 1990s and 2000s by many researchers. Michael Reisenberger and Carlo Rovelli introduced the basic idea in 1997. John Barrett and Louis Crane developed an influential early model. Laurent Friedel and Kirill Krasnov made important contributions. And the model that is most widely studied today, known as the EPRL-FK model, after its developers, was completed around 2008 by Jonathan Engel, Roberto Pereira, Carlo Rovelli, Laurent Friedel, and Kirill Krasnov. The EPRL-FK model assigns specific amplitudes to spin foams. In quantum mechanics, we compute the probability of various outcomes by calculating amplitudes, which are complex numbers, and then squaring their magnitudes. Similarly, the EPRL-FK model assigns a complex amplitude to each spin foam configuration. By summing over all possible spin foams weighted by their amplitudes, we can calculate the probability for space to transition from one quantum state to another. This is closely analogous to the Feynman path integral in ordinary quantum mechanics. In Feynman's approach, the amplitude for a particle to go from point A to point B is computed by summing over all possible paths the particle could take, with each path weighted by a phase factor. Most of the paths cancel out due to destructive interference, leaving the classical path as the dominant contribution. But quantum effects arise from the sum over all paths, including the wiggly, non-classical ones. In the spin foam approach, we similarly sum over all possible spin foams, connecting an initial spin network to a final spin network. Each spin foam represents a possible history of quantum spacetime, a way for space to evolve from its initial state to its final state. Most spin foams contribute little due to cancellation, but the sum over all of them gives the quantum mechanical transition amplitude. The vertices of a spin foam are particularly important. They represent events where the structure of space changes, where links of the spin network are created or destroyed, where the topology of the network transforms. At each vertex, a specific amplitude is assigned, depending on the spins and intertwiners of the adjacent faces and edges. These vertex amplitudes are the fundamental building blocks of spin foam dynamics. In the EPRL-FK model, the vertex amplitude has been computed explicitly. It involves mathematical objects called Wigner symbols, which describe how angular momenta combine in quantum mechanics, along with additional factors that ensure the correct behavior in various limits. The calculation is technically challenging, but the result is a concrete formula that can be evaluated numerically. One of the most exciting developments in recent years has been the numerical study of spin foam amplitudes. Using computer calculations, researchers have been able to evaluate the vertex amplitude for various configurations and study its properties. These calculations have confirmed that, in an appropriate limit, the EPRL-FK model reproduces the classical dynamics of general relativity. When the spin labels are large, corresponding to nearly classical geometries, the spin foam amplitudes are dominated by configurations that satisfy Einstein's equations. The discrete quantum geometry of spin foams gives way to the smooth curved spacetime of general relativity. This is an essential check on the theory. Loop quantum gravity is supposed to be a quantum theory of gravity, a deeper description that reduces to general relativity in an appropriate limit. The fact that this correspondence has been verified numerically gives confidence that the theory is on the right track. But the spin foam approach also predicts genuinely quantum effects, deviations from classical general relativity that would become significant at the Planck scale. Near singularities where classical gravity breaks down, the spin foam description is expected to remain well defined. The quantum dynamics would prevent the formation of true singularities, replacing them with quantum bounces and other phenomena that follow naturally from the discrete structure of spacetime. We will explore these predictions in the sections on cosmology and black holes. The spin foam formulation also provides insight into the nature of time in quantum gravity. In the canonical approach based on spin networks, time is problematic. The Wheeler-DeWitt equation has no time variable. The theory seems to describe a frozen, timeless universe. This is the notorious problem of time in quantum gravity. The spin foam approach offers a partial resolution. Time emerges from the spin foam dynamics as the direction of evolution from one spin network to another. It is not a background parameter, but a consequence of the quantum gravitational dynamics. The ordering of events, the flow from past to future, arises from the structure of the spin foam itself. This emergence of time from timelessness is one of the most philosophically intriguing aspects of loop quantum gravity. It suggests that time as we experience it is not fundamental but emergent, a feature of the coarse-grained, macroscopic description rather than the underlying quantum reality. At the Planck scale, there may be no time in the usual sense, just a web of quantum relations from which our familiar notion of temporal flow eventually emerges. The quantization of geometry, areas and volumes. Let us examine more closely what it means for geometry itself to be quantized. This is one of the most striking and counterintuitive predictions of loop quantum gravity, and understanding it properly requires some careful thought about what geometric quantities actually are and how they are measured. In everyday life, we take for granted that areas and volumes can be any size. A tabletop might be exactly 1 square meter, or 1.1 square meters, or any other value. The areas form a continuous spectrum. You can always imagine an area halfway between any two given areas, and there is no minimum possible area. The same goes for volumes, for lengths, for any geometric quantity. This continuous nature of geometry is deeply embedded in our mathematical frameworks. Euclidean geometry, the geometry we learn in school, describes points, lines, and planes that can be positioned and sized with arbitrary precision. Riemannian geometry, the curved generalization that Einstein used for general relativity, inherits this continuous character. The metric tensor, which encodes distances and angles, is a smooth function that varies continuously from point to point. But loop quantum gravity challenges this assumption. When we quantize gravity using the methods of quantum mechanics, the operators corresponding to geometric quantities like area and volume turn out to have discrete spectra. Just as the energy of a hydrogen atom can only take certain discrete values, so too can the area of a surface or the volume of a region. The area operator was one of the first geometric quantities to be studied in loop quantum gravity. Ravelli and Smolin, along with Ashtekar and Lewandowski, computed its spectrum in the mid-1990s. The result was beautiful and surprising. Consider a surface crossing through the spin network. Each link of the spin network that crosses the surface contributes to the total area. If a link carries spin j, its contribution to the area is proportional to the square root of j times j plus 1. The proportionality constant involves the Planck area, about 10 to the negative 70 square meters, and a dimensionless parameter called the Emirzi parameter, denoted by the Greek letter gamma. The total area of the surface is the sum of the contributions from all the links that cross it. Since each contribution is discrete, the total area is also discrete. The possible values form a discrete spectrum, a ladder of allowed areas separated by gaps. The smallest non-zero area is achieved when a single link of spin 1/2 crosses the surface. This minimum area is approximately equal to the Planck area multiplied by the square root of 3 divided by 2, further multiplied by the Emirzi parameter. For typical values of the Emirzi parameter, the minimum area is of order the Planck area, roughly 10 to the negative 70 square meters. This is unimaginably small by everyday standards, but represents a genuine physical lower limit. The area gap, the difference between zero area and the minimum non-zero area, has profound implications. It means that surfaces cannot be arbitrarily small. There is a minimum meaningful size for any two-dimensional region. Below this scale, the concept of area loses meaning. Space is fundamentally granular. The volume operator is more complicated but shares the essential feature of discreteness. Volumes are associated with nodes of the spin network rather than links. The volume of a region depends on the intertwiners at the nodes contained within that region. Like area, volume has a discrete spectrum with a minimum non-zero value, roughly the Planck volume. The volume spectrum has been studied extensively by researchers, including Johannes Brunnemann and Tiemann, who computed the eigenvalues for various configurations of nodes and links. The spectrum has rich structure with eigenvalues depending on the spins and intertwiners in intricate ways, but the key feature is always discreteness. Volumes come in discrete quanta. The Emirzi parameter plays an interesting role in these results. It appears in the formula for area eigenvalues, but affects only the overall scale, not the qualitative feature of discreteness. The Emirzi parameter is a free parameter in loop quantum gravity, analogous to certain coupling constants in other theories. Its value must be determined either by experiment or by some theoretical consistency requirement. Remarkably, the Emirzi parameter can be fixed by requiring that loop quantum gravity correctly reproduce the entropy of black holes. As we will discuss later, loop quantum gravity provides a microscopic derivation of the Bekenstein-Hawking entropy formula for black holes. This derivation only gives the correct numerical factor if the Emirzi parameter takes a specific value, approximately 0.2375. This is a non-trivial consistency check on the theory. What are the physical consequences of quantized geometry? Most directly, it resolves the singularity problems that plague classical general relativity. In Einstein's theory, singularities arise when curvature becomes infinite, when densities and temperatures exceed all bounds, when the equations break down completely. These singularities occur at the center of black holes and at the Big Bang. But if there is a minimum area and volume, as the theory predicts, curvatures cannot become truly infinite. When matter is compressed to the Planck density, the quantum geometry would prevent further compression. This implies that the singularity would be avoided, replaced by a quantum bounce or some other regular behavior. The physics would remain well defined even in the most extreme circumstances, which could resolve one of the deepest puzzles in gravitational physics. The quantization of geometry also provides a natural cutoff for ultraviolet divergences. In quantum field theory, infinities arise when we sum over contributions from arbitrarily small distances. These infinities must be absorbed through a process called renormalization, but gravity cannot be renormalized in the standard way. The infinities persist and become worse at higher orders of approximation. Loop quantum gravity sidesteps this problem entirely. If there is a minimum length, there are no contributions from distances. smaller than the Planck length. The sums that would otherwise diverge are automatically finite. The theory is ultraviolet complete, not because of some mathematical trick, but because space-time itself has a minimum scale. From a philosophical perspective, the quantization of geometry represents a profound shift in our understanding of space. For millennia, space has been conceived as a continuous, infinitely divisible void. Euclid's geometry, Descartes' coordinates, Newton's absolute space, Einstein's space-time, all share the assumption of continuity. Loop quantum gravity tells us that this assumption is wrong, or at least incomplete. At the deepest level, space is made of discrete pieces, quanta of geometry, woven together into the fabric we experience. This discreteness is not directly observable with current technology. The Planck scale is so far below our experimental reach that the quantum nature of space has no practical consequences for everyday physics. But in principle, the discreteness is there, underlying everything we see and touch. Every meter of space contains roughly 10 to the 35 Planck lengths. Every cubic meter contains roughly 10 to the 105 Planck volumes. These astronomical numbers of tiny quanta add up to produce the apparently continuous space around us. It is a humbling picture. The smooth stage on which we live our lives, the three-dimensional arena in which all events occur, is ultimately an illusion, or rather, an emergent phenomenon. Like the smoothness of a liquid that emerges from the jittering of molecules, the continuity of space emerges from the quantum dance of spin networks. At the foundation, there is only discreteness, only the atoms of geometry combining and recombining according to the laws of quantum gravity. Loop quantum cosmology, the Big Bounce, and the origin of the universe. One of the most exciting applications of loop quantum gravity is to cosmology, the study of the universe as a whole. When we apply the principles of quantized spacetime to the earliest moments of cosmic history, we discover something remarkable in the mathematics. The Big Bang singularity, that moment of supposedly infinite density and temperature at the origin of time, simply does not exist in this framework. In its place, loop quantum cosmology predicts a quantum bounce, a transition from a previously contracting universe to our present expanding one. This prediction addresses one of the most profound mysteries in physics. Classical general relativity tells us that if we run the clock backward, the universe contracts, becomes hotter and denser, until finally, at a finite time in the past, it reaches a singularity. At this singularity, the density becomes infinite, the temperature becomes infinite, the curvature of space-time becomes infinite. The equations of general relativity break down completely. We cannot say what happened before the Big Bang because, in the classical theory, there was no before. Time itself began at the singularity. This singularity has troubled physicists since it was first rigorously proven by Roger Penrose and Stephen Hawking in the 1960s. A singularity represents a breakdown of physics, a place where our theories simply fail. Most physicists believe that singularities are artifacts of using classical general relativity in regimes where quantum effects should dominate. A proper quantum theory of gravity, they reasoned, should resolve the singularity and tell us what really happens at extremely high densities. Loop quantum cosmology, developed beginning in the early 2000s primarily through the work of Martin Bojewald, and significantly advanced in 2006 by Abhay Ashtekar, Tomasz Pawlowski, Parampreet Singh, and many others, provides exactly such a resolution. The key insight is that the quantum geometry effects of loop quantum gravity become important at the Planck density, roughly 10 to the 93 grams per cubic centimeter. This is an almost inconceivably large density, far exceeding anything found in ordinary matter or even in neutron stars. But the early universe, in the standard Big Bang scenario, would have exceeded this density as we approach the initial singularity. When the quantum geometry effects are included, something remarkable happens. The universe does not collapse to infinite density. Instead, when the density approaches the Planck density, a new kind of repulsive force emerges from the quantum nature of spacetime. This force is not mediated by any particle or field. It is an intrinsic effect of the discrete, quantized structure of space at the Planck scale. As the universe tries to shrink below a certain minimum volume, the quantum pressure pushes back, causing the universe to bounce rather than collapse. The technical details of how this bounce occurs involve the modification of the fundamental equations of cosmology. In classical general relativity, the evolution of a homogeneous and isotropic universe is governed by the Friedmann equations, which relate the expansion rate of the universe to its energy density. In loop quantum cosmology, these equations are modified by quantum corrections that become significant at high densities. The modified Friedmann equation includes a term proportional to the ratio of the energy density to the maximum density. When the density is much smaller than the Planck density, this correction is negligible, and the equations reduce to the classical Friedmann equations. General relativity is recovered as an excellent approximation. But as the density approaches the Planck density, the correction becomes large and eventually causes the expansion rate to vanish and then reverse sign. The contraction ends and expansion begins. This is the quantum bounce. The bounce occurs at a critical density that calculations suggest is roughly 40% of the Planck density, though the precise value depends on the details of the model. At this moment, the universe has a minimum volume, still vastly larger than the Planck volume, but far smaller than anything in our current observable universe. The universe passes smoothly through this minimum, transitioning from contraction to expansion. There is no singularity, no breakdown of physics, no moment where time begins. The universe exists both before and after the bounce. What does this mean for our understanding of cosmic origins? It suggests that our Big Bang was not the absolute beginning of everything. It was the end of a previous contracting phase, and the beginning of our current expanding phase. Before our Big Bang, there was another universe, contracting toward the moment we call the Big Bang. At that moment, the quantum bounce occurred, and our present expanding universe began. This picture has been called the Big Bounce, in contrast to the classical Big Bang. If these predictions hold, it would represent a paradigm shift in cosmology. Instead of a creation from nothing, a first moment of time, we would have an eternal universe that cycles through phases of expansion and contraction. Each bounce would be a transition, a cosmic transformation, but not a beginning or an end in any absolute sense. The mathematics consistently produces this result, and future observations may eventually provide the empirical evidence needed to confirm or refute this extraordinary possibility. Numerical simulations have confirmed this picture in remarkable detail. Researchers have evolved the quantum state of the universe, through the bounce, showing that a large classical universe in contraction indeed bounces into a large classical universe in expansion. The simulations track not just the average behavior, but the quantum fluctuations, verifying that the effective equations provide an excellent approximation to the full quantum dynamics. Interestingly, not all information survives the bounce. Some properties of the pre-bounce universe are preserved, while others are lost due to quantum uncertainty. The volume at the bounce, for instance, depends on properties of the collapsing universe, but detailed information about the quantum state can be scrambled by the bounce. This is consistent with what we would expect from quantum mechanics, where the uncertainty principle limits what can be known simultaneously about conjugate variables. Loop quantum cosmology also provides insights into the very early universe immediately after the bounce. One of the great puzzles of standard cosmology is the horizon problem. Why is the cosmic microwave background radiation so uniform across the sky, even between regions that apparently could never have been in causal contact? The standard solution invokes cosmic inflation, a period of exponentially rapid expansion in the early universe that would have stretched initially tiny regions to cosmic scales. Loop quantum cosmology offers a complementary perspective. The quantum bounce itself provides some of the conditions usually attributed to inflation. The universe, just after the bounce, is already in a coherent, homogeneous state because it emerged from the smooth quantum geometry at the bounce. Furthermore, some versions of loop quantum cosmology naturally incorporate a period of superinflation immediately, hot, after the bounce, driven by the same quantum geometry effects that caused the bounce itself. Recent work has focused on deriving observational predictions from loop quantum cosmology. The primordial perturbations that seeded the formation of galaxies and the cosmic microwave background anisotropies are modified by quantum gravity effects. While these modifications are typically small, they might leave detectable signatures in precision cosmological observations. Researchers have calculated the power spectrum of primordial perturbations in loop quantum cosmology and compared it to the predictions of standard inflationary cosmology. The most distinctive prediction is a suppression of power at the largest scales, corresponding to modes that would have been affected by the quantum bounce. These modes would have wavelengths comparable to the entire observable universe. Intriguingly, current observations from missions like Planck have shown some tentative evidence that could be consistent with such a suppression. While other explanations remain possible, this alignment between prediction and observation suggests that future measurements, particularly of the cosmic microwave background polarization, could provide crucial tests of loop quantum cosmology. The black hole singularity, the other major singularity predicted by classical general relativity, is also addressed by loop quantum gravity. When a massive star collapses at the end of its life, general relativity predicts that it forms a black hole with a singularity at its center, a point of infinite density where matter is crushed out of existence. But just as the quantum bounce replaces the Big Bang singularity in cosmology, a similar mechanism operates inside black holes. As collapsing matter approaches the Planck density, the quantum geometry effects would push back, preventing the formation of a true singularity. According to the theory, the matter would bounce, and the black hole interior would be modified, Recent theoretical work by Carlo Rovelli, Francesca Vidotto, and collaborators has proposed a specific scenario called the Planck star. In this picture, the matter that falls into the black hole does not disappear at a singularity, but instead collects in a stable configuration at Planck density, a Planck star, supported against further collapse by quantum pressure. Based on what we understand about the quantum geometry at these extreme densities, such a configuration could be stable over cosmological timescales. The Planck star, if it exists, would be incredibly small by astronomical standards, but still finite, not a point. Over extremely long times, comparable to the lifetime of the universe, the black hole would slowly evaporate through Hawking radiation. Eventually, the Planck star would be revealed, potentially in an explosive event, as the stored information finally escapes. This scenario offers a possible resolution to the black hole information paradox, the puzzle of what happens to information that falls into a black hole. Black hole physics and the mystery of entropy. Black holes are among the most mysterious objects in the universe, and they provide a crucial testing ground for any theory of quantum gravity. Loop quantum gravity has achieved remarkable success in explaining certain properties of black holes, particularly their entropy, while also offering new perspectives on their internal structure and ultimate fate. The story begins with Stephen Hawking's famous discovery in 1974 that black holes are not completely black. They emit thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation has a characteristic temperature inversely proportional to the black hole's mass. For a black hole with the mass of the Sun, the temperature is a tiny fraction of a degree above absolute zero, far too cold to detect. But for microscopic black holes, the temperature can be enormously high. Hawking's discovery implies that black holes have entropy. In thermodynamics, any object with a temperature must have entropy, a measure of the number of microscopic configurations compatible with its macroscopic properties. Jacob Bekenstein had already proposed, based on thought experiments, that black holes should have entropy proportional to their surface area rather than their volume. Hawking's calculation confirmed this and pinned down the proportionality constant. The Bekenstein-Hawking entropy formula states that the entropy of a black hole equals 1/4 of its horizon area, measured in Planck units. This formula is deeply puzzling from the perspective of classical physics. Normally, entropy is proportional to volume, not area. A box of gas has more entropy if the box is bigger. But black holes are different. Their entropy scales with the area of the horizon, the surface of no return surrounding the black hole. What could this possibly mean? What are the microscopic degrees of freedom that account for this entropy? Where do they live? Loop quantum gravity provides a compelling answer. In the quantum theory, the horizon of a black hole is a physical surface crossed by the links of spin networks. Each link that crosses the horizon contributes to the horizon's area, as we discussed earlier. The quantum state of the horizon is therefore characterized by the collection of spins on the links that pierce it. But here is the key insight. There are many different ways to assign spins to the links that give the same total horizon area. Different spin configurations can have the same macroscopic area, but differ in their microscopic details. The number of such configurations is the exponential of the entropy. The entropy counts the number of distinct quantum states of the horizon that are consistent with the macroscopic area. This calculation was first performed in the mid-1990s by Rovelli, Krasnov, Ashtekar, Baez, and collaborators. They showed that the number of spin network states compatible with a given horizon area grows exponentially with the area. Taking the logarithm gives an entropy proportional to the area, in agreement with the Bekenstein-Hawking formula. But there was a catch. The coefficient of proportionality depended on the Emirzi parameter, the free parameter that enters the area spectrum. To get exactly 1/4, as the Bekenstein-Hawking formula requires, the Emirzi parameter had to take a specific value, approximately 0.2375. This was either an embarrassment, suggesting that the theory had a free parameter that must be tuned by hand, or a triumph, suggesting that black hole thermodynamics fixes a previously undetermined parameter. Most practitioners have come to view it as the latter. The Emirzi parameter is now seen as a prediction of loop quantum gravity, determined by the requirement of consistency with black hole thermodynamics. The same value of the Emirzi parameter that gives the correct entropy for Schwarzschild black holes also works for charged and rotating black holes, a non-trivial consistency check. More recently, researchers have made progress on deriving the Bekenstein-Hawking formula without any dependence on the Emirzi parameter. These calculations, which use the full covariant spin foam dynamics rather than the canonical approach, suggest that the entropy formula can be obtained more naturally in certain frameworks. The issue is subtle and still under active investigation, but there is growing confidence that loop quantum gravity correctly accounts for black hole entropy. The calculation also predicts quantum corrections to the entropy. The leading term is the Bekenstein-Hawking formula, proportional to the area, but there are subleading corrections that go as the logarithm of the area, then as constants, and so on. These corrections are minuscule for astrophysical black holes, but would be significant for microscopic black holes or in the final stages of black hole evaporation. The logarithmic correction has been computed in loop quantum gravity, and it agrees with calculations from other approaches, including string theory. This agreement across different theoretical frameworks is encouraging. It suggests that the logarithmic correction is a robust feature of quantum gravity, independent of the details of any particular approach. Beyond entropy, loop quantum gravity offers a new picture of the interior of black holes. In classical general relativity, the singularity at the center of a black hole is an absolute endpoint for anything that falls in. Space and time end there. Objects are crushed to infinite density and effectively destroyed. This is deeply troubling, not only because of the mathematical breakdown, but because it suggests that information is permanently lost. The information paradox, first articulated by Hawking, points out a conflict between quantum mechanics and general relativity regarding black holes. Quantum mechanics is fundamentally unitary, meaning that information about the initial state of a system is always preserved in its final state. But if information falls into a black hole, and the black hole eventually evaporates completely through Hawking radiation, where does the information go? If the information is destroyed at the singularity, quantum mechanics is violated. If the information escapes in the Hawking radiation, how is this possible given that nothing can escape from inside the event horizon? Loop quantum gravity may offer a path toward resolving this paradox by eliminating the singularity. If the interior of the black hole contains a Planck star rather than a singularity, information would not be destroyed, but merely stored in an extremely compressed form. As the black hole evaporates, this information could eventually be released. Based on what we know about quantum mechanics, this would preserve unitarity while still allowing for the dramatic gravitational collapse that forms black holes. The details of exactly how information might be encoded and released are still being worked out, but the conceptual framework appears promising. The Planck star scenario also has implications for the ultimate fate of black holes. In the classical picture, a black hole evaporates completely through Hawking radiation, eventually disappearing entirely in a final burst. In the loop quantum gravity picture, when the black hole has shrunk to roughly the Planck mass, the quantum core is revealed. The transition from black hole to Planck star might involve a quantum tunneling process, similar to radioactive decay. A provocative suggestion put forward by Rovelli and Vedato is that this tunneling could happen much faster from the perspective of an observer inside the black hole than it appears from outside, due to extreme time dilation near the horizon, a process that takes only a fraction of a second from the inside perspective might take the entire age of the universe from the outside perspective. If this picture is correct, it could explain why we have not observed the explosive death throes of ancient primordial black holes. The mathematics of general relativity certainly allows for such extreme time dilation, and the quantum tunneling mechanism draws on well-established principles. Whether nature actually works this way remains an open and fascinating question. Loop quantum gravity and string theory. Two paths to quantum reality. Loop quantum gravity does not exist in isolation. It is one of several major research programs attempting to construct a quantum theory of gravity. The most prominent alternative is string theory, and comparing these two approaches illuminates the deep questions at stake in quantum gravity research. String theory began in the late 1960s as a theory of the strong nuclear force before being reimagined as a theory of quantum gravity in the mid-1970s. The core idea is that fundamental particles are not point-like objects, but tiny vibrating strings. Different vibrational modes of the string correspond to different particles. Remarkably, one of these modes has the properties of the graviton, the hypothetical quantum of the gravitational field. String theory is thus automatically a theory of gravity. Over the decades, string theory has developed into a rich and sophisticated framework. It has unified gravity with the other fundamental forces, at least in principle. It has led to deep mathematical discoveries with applications far beyond physics. It has spawned ideas like extra dimensions, brains, and the multiverse that have captured the public imagination. But string theory is fundamentally different from loop quantum gravity in its approach. String theory is background dependent. Strings propagate through a pre-existing spacetime, typically with 10 dimensions. The dynamics of the strings occurs against this fixed backdrop. The spacetime itself is not quantized directly. Gravity emerges from the string dynamics, but the background remains classical. Loop quantum gravity, as we have seen, is background independent. There is no pre-existing spacetime. Space and time emerge from the quantum dynamics of spin networks and spin foams. The discreteness of geometry is a prediction of the theory, not an input. This difference in philosophy leads to very different mathematical structures and physical predictions. String theory requires extra dimensions beyond the four we observe. The consistency of the quantum theory demands precisely 10 dimensions for superstrings, or 11 for M theory, the hypothetical master theory that unifies different string theories. These extra dimensions must be hidden somehow, typically by being compactified into tiny geometric shapes at each point of ordinary spacetime. The geometry and topology of these compact dimensions determine the properties of particles and forces we observe. Loop quantum gravity, by contrast, works in 4 dimensions without extra dimensions. The 3 dimensions of space and 1 dimension of time that we directly experience are sufficient. There is no need for hidden geometries or compactification. This is arguably more economical, requiring fewer assumptions. String theory also requires supersymmetry, a hypothetical symmetry relating bosons and fermions. Supersymmetry predicts that every known particle has a heavier superpartner that we have not yet observed. Despite extensive searches at the Large Hadron Collider and elsewhere, no evidence for supersymmetry has been found. This is not definitive proof against string theory, since the superpartner masses could be beyond current experimental reach, but it is a disappointment. Loop quantum gravity does not require supersymmetry. It can accommodate supersymmetric matter if it exists, but the basic structure of the theory does not depend on it. If supersymmetry is never discovered, string theory will be in serious trouble, while loop quantum gravity will be unaffected. Perhaps the most significant difference concerns what the theories are trying to achieve. String theory is ambitious. It aims to be a theory of everything, unifying gravity with all other forces and explaining all particles and their properties. The standard model of particle physics, with its quarks and leptons and gauge bosons, should emerge from string theory as a low-energy approximation. The masses and coupling constants that are free parameters in the standard model should be calculable from string theory. Loop quantum gravity is more modest. It aims to be a quantum theory of gravity and nothing more. It does not attempt to unify gravity with other forces. It does not explain why particles have the masses and charges they have. The standard model is simply coupled to quantum gravity as external input. The matter sector is treated as given rather than derived. This difference in scope can be seen as either a strength or a weakness of loop quantum gravity. On one hand, the modest goals make the theory more tractable. There are fewer moving parts, fewer ways for things to go wrong. On the other hand, a theory of everything would be more powerful and explanatory if it could be found. The trade-off between ambition and tractability is a recurring theme in theoretical physics. Neither theory has made predictions that have been confirmed by experiment. This is not surprising, since both theories primarily operate at the Planck scale, far beyond current experimental reach. But it means that neither theory has achieved the gold standard of scientific validation, agreement with observation. Both remain speculative, supported by mathematical consistency and theoretical beauty, rather than empirical evidence. String theory has struggled with what is called the landscape problem. There are an enormous number of possible string theory vacua, different ways of compactifying the extra dimensions that lead to different low-energy physics. Estimates of the number of possibilities range from 10 to the 500 to infinity. Without some principle to select among these vacua, string theory cannot make definite predictions for particle physics. Loop quantum gravity has its own challenges. The dynamics of the theory, how spin networks evolve through spin foams, is not completely understood. Different proposals for the dynamics lead to different predictions. The semi-classical limit, showing that smooth spacetime emerges from quantum gravity, has been demonstrated in certain regimes, but not proven in full generality. These are serious obstacles, though no more serious than those facing string theory. There have been recent suggestions that the two approaches might be related, that they could be different descriptions of the same underlying reality. The ADAS-CFT correspondence, a deep connection discovered in string theory between gravity in certain curved spacetimes and quantum field theory on their boundaries, has partial analogues in loop quantum gravity. If these connections deepen, we might eventually find that the apparent rivalry between loop quantum gravity and string theory dissolves into a more unified understanding. Challenges, criticisms, and the road ahead. No scientific theory is beyond criticism, and loop quantum gravity is no exception. It faces significant challenges that must be overcome if it is to become a complete and confirmed theory of quantum gravity. Understanding these challenges is as important as appreciating the theory's successes. The most significant challenge concerns the semi-classical limit. Loop quantum gravity is fundamentally a theory of quantum spacetime at the Planck scale, but we experience classical spacetime at ordinary scales. The theory must reproduce general relativity as an approximation valid for large, smooth, nearly classical geometries. This is not just a technical requirement, but a fundamental consistency check. If loop quantum gravity cannot recover Einstein's equations in the appropriate limit, it fails as a theory of gravity. Progress has been made on this front. The spin foam calculations mentioned earlier show that for large spins, the amplitudes are dominated by geometries satisfying the Einstein equations. Numerical studies confirm this behavior, but a complete, rigorous proof that smooth spacetime emerges from the fundamental quantum theory is still lacking. The technical difficulties are formidable, involving limits of discrete sums that become continuous integrals, emergence of smooth manifolds from combinatorial structures, and appearance of local Lorentz symmetry from a fundamentally discrete theory. Related to the semi-classical limit is the problem of low-energy physics. Even if classical spacetime emerges, the theory must also accommodate the standard model of particle physics. Electrons, quarks, photons, gluons, all the particles we observe must somehow fit into the loop quantum gravity framework. This coupling of matter to quantum gravity is not fully understood. There are proposals for how to include fermions and gauge fields in the spin network formalism, but they face technical difficulties, notably the fermion doubling problem, where naive attempts to include fermions produce unwanted extra particles. Another challenge is the uniqueness of the dynamics. In the covariant spin foam approach, there are several different models for the quantum dynamics, including the Barrett-Crane model and the EPRL-FK model. These models make different predictions in certain regimes. Which one is correct? Is there a unique quantum dynamics, or are there multiple consistent possibilities? These questions remain open. Critics of loop quantum gravity have raised more fundamental objections. Some argue that the theory's background independence is not an advantage, but a handicap. Without a fixed background, it is difficult to formulate scattering amplitudes, calculate transition probabilities, or make other standard predictions of quantum field theory. The technology that has proven so powerful for the Standard Model and for string theory is not directly applicable. Practitioners must develop new methods, which takes time and effort. Others question whether the discrete spectrum of geometric operators is a genuine prediction or an artifact of the quantization procedure. The spectrum depends on certain choices made in constructing the quantum theory, such as the particular representation of the holonomy flux algebra. Different choices might lead to different spectra. The robustness of the discreteness prediction has been established mathematically through uniqueness theorems, but whether this mathematical uniqueness reflects physical reality remains a matter of debate. Experimental tests of loop quantum gravity are extremely challenging. The Planck scale is roughly 17 orders of magnitude beyond current accelerator energies. Direct observation of discrete spacetime seems impossible with any foreseeable technology. However, there are indirect possibilities. Some approaches to quantum gravity, including certain versions of loop quantum gravity, predict tiny violations of Lorentz symmetry, the symmetry that underlies special relativity. These violations could cause light of different energies to travel at slightly different speeds. By observing gamma rays from distant astrophysical sources like gamma-ray bursts, physicists can search for energy-dependent delays. So far, no such violations have been detected. Observations of gamma-ray bursts, particularly the exceptionally bright event GRB 21009A in 2022, have placed stringent limits on such effects, ruling out certain classes of quantum gravity models. Importantly, many practitioners of loop quantum gravity argue that Lorentz violations are not a necessary prediction of the theory. Carlo Rovelli and others maintain that a properly formulated version of loop quantum gravity is fully compatible with Lorentz symmetry, and that the null results of astrophysical tests are not problematic. The debate continues with different researchers holding different views on what loop quantum gravity actually predicts. Cosmological observations offer another potential window. The primordial perturbations that seeded structure formation and the cosmic microwave background anisotropies might carry signatures of quantum gravity effects from the early universe. Loop quantum cosmology predicts specific modifications to the power spectrum at the largest scales, as mentioned earlier. Future missions with greater precision might detect these effects or rule them out. Black hole physics could also provide observational opportunities. If the quantum structure predicted by LQG affects the horizon, it could modify the spectrum of Hawking radiation, introducing discrete lines or other features that differ from the perfectly thermal spectrum predicted classically. Based on what we understand about quantum geometry, such modifications would be most pronounced for small black holes. If primordial black holes exist and are currently evaporating, such effects might conceivably be detectable. The final stages of black hole evaporation, when the black hole shrinks to near the Planck mass, would be particularly dramatic, potentially releasing stored information in a characteristic burst. Gravitational wave astronomy, inaugurated by the LIGO detections in 2015, opens new possibilities for probing strong gravity. The merger of black holes and neutron stars generates gravitational waves that carry information about the extreme conditions near the event horizon. While current observations are consistent with general relativity, future detectors with greater sensitivity might reveal quantum gravity effects. The ring-down signal following a black hole merger is particularly sensitive to the near-horizon geometry and could potentially show signatures of quantum spacetime structure. The philosophical implications of discrete spacetime as we near the end of our journey, let us reflect on what loop quantum gravity means for our understanding of reality. The theory makes specific technical predictions, but it also carries profound philosophical implications about the nature of space, time, and existence. The most immediate implication is that space is not what we thought it was. For centuries, scientists and philosophers conceived of space as a continuous, infinitely divisible void. Newton imagined absolute space as a fixed stage on which physics occurs. Leibniz argued for a relational view, but still assumed continuity. Einstein dynamized space-time, making it responsive to matter and energy, but preserved its smooth, continuous character. Loop quantum gravity breaks with all these traditions. Space is discrete, granular, made of finite pieces rather than infinitely divisible continuum. This discreteness challenges our intuitions in fundamental ways. We are used to thinking that between any 2 points, there is always another point. Between any 2 numbers, there is always another number. But if space is discrete, this is not true at the Planck scale. There is a smallest distance, and nothing lies between points separated by that distance. The concept of in-between loses meaning at the finest scales. Time undergoes a similar transformation. The smooth flow of time, the river carrying us from past to future, is an emergent phenomenon. At the fundamental level, time might not exist at all in the usual sense. The Wheeler-DeWitt equation has no time variable. Spin foams describe relations between spatial geometries without reference to an external clock. Time, like space, emerges from the quantum gravitational dynamics rather than being given a priori. This emergence of time from timelessness is one of the most challenging aspects of quantum gravity to understand intuitively. We experience time so directly, so unavoidably, that imagining its absence seems almost impossible. Yet the mathematics of loop quantum gravity suggests that this is precisely what we must do. At the Planck scale, there is no before and after in any familiar sense. There are just quantum relationships, patterns of correlation between spin network states, from which the appearance of temporal flow eventually arises. The relational character of loop quantum gravity also has philosophical significance. In this theory, there is no absolute space or time, no fixed backdrop against which physics unfolds. All that exists are relationships between physical entities. The location of an event has meaning only relative to other events. The time of an occurrence is defined only in relation to other occurrences. There is no God's eye view, no external standpoint from which to observe the universe. Reality is thoroughly relational. This relational view resonates with certain philosophical traditions, particularly process philosophy and the work of Alfred North Whitehead. It also connects to interpretations of quantum mechanics that emphasize the role of observation and information. Carlo Rovelli has developed these connections explicitly in his relational interpretation of quantum mechanics, arguing that quantum states themselves are relational, defined only with respect to particular observers or reference systems. The discreteness of spacetime also raises questions about the nature of continuity in mathematics. Mathematical analysis, the study of calculus and real numbers, assumes the continuity of the real line. Every point can be specified by an infinite decimal expansion. Between any two numbers are infinitely many others. But if physical space is discrete, what is the status of these mathematical structures? Are they mere abstractions with no physical correlate? Or do they capture some aspect of reality beyond what current physics describes? Some physicists have speculated that the mathematical continuum might itself be an emergent phenomenon, arising from more fundamental discrete structures through some form of limit or approximation. Others maintain that mathematics describes a Platonic realm independent of physical reality. The debate mirrors long-standing controversies in the philosophy of mathematics and gains new urgency from the physics of quantum gravity. There are also implications for our understanding of locality. In classical physics and ordinary quantum field theory, interactions are local. Things can only directly affect their immediate neighbors. Distant influences require chains of local interactions or the propagation of fields through space. But if space is discrete, made of nodes and links, the very notion of neighborhood must be reconsidered. What does local mean in a spin network? The connections between nodes define adjacency, but these connections can be arbitrarily long in any embedding into continuous space. Locality becomes a relational property, defined by the graph structure rather than by distance in a background space. These considerations have led some researchers to explore violations of locality at the Planck scale, with potentially observable consequences. Quantum entanglement might be more naturally described in a discrete spacetime framework. The non-local correlations that characterize entangled states could reflect the underlying graph structure of quantum spacetime, where nodes can be directly connected regardless of their separation in an emergent classical geometry. If this interpretation holds, it would provide a deep explanation for one of quantum mechanics' most puzzling features. Finally, loop quantum gravity has implications for the question of cosmic origins. If the Big Bang is replaced by a quantum bounce, then time extends infinitely into the past, or at least into a regime we cannot access from our side of the bounce. The question of why there is something rather than nothing remains unanswered, but it takes a different form. Instead of asking why the universe began, we might ask why it bounces, why it cycles through phases of expansion and contraction. This could imply that the mystery of existence persists, but the specific question has shifted in a profound way. These philosophical implications follow naturally from the physics, though they extend beyond what the current mathematical formalism definitively establishes. But they are grounded in the physics, the discreteness of geometry, the emergence of time, the relational character of spacetime, all flow from the mathematical structure of loop quantum gravity. If the theory is correct, these implications follow. Understanding quantum gravity is not just a technical exercise, but a revision of our deepest concepts about the nature of reality. Conclusion: the fabric of space and time. We have traveled a long way tonight, from the broad puzzles of reconciling general relativity with quantum mechanics, down to the Planck scale, where space and time become granular, through the mathematical structures of spin, networks, and spin foams, and outward again to the cosmological implications of a bouncing universe and the quantum interiors of black holes. Loop quantum gravity offers a radical vision of reality. Space is not smooth but discrete. composed of tiny quanta of geometry woven together in a vast network. Time does not flow continuously, but emerges from a deeper, timeless realm of quantum relationships. The singularities that plague classical general relativity at the Big Bang and at the centers of black holes are resolved by quantum effects that prevent infinite densities from ever forming. This vision is not yet confirmed by experiment. The Planck scale remains far beyond our direct observational reach. But the mathematical structure of loop quantum gravity is coherent and compelling. It predicts the quantization of geometry from first principles without putting in discreteness by hand. It derives the entropy of black holes from counting quantum states. It resolves the singularity problem that has troubled physicists for decades. The competition with string theory remains unresolved. Both approaches have strengths and weaknesses. Both face significant challenges. Both offer profound insights into the possible nature of quantum spacetime. Perhaps one will eventually prove correct, while the other is abandoned. Perhaps they will turn out to be different perspectives on the same underlying reality. Perhaps both will be superseded by something we have not yet imagined. What we can say with confidence is that the effort to understand quantum gravity has led us to reconsider the most basic concepts in physics: space, time, continuity, locality, the flow of history. All must be rethought in light of what we are learning. Even if the specific details of loop quantum gravity turn out to need revision, the conceptual framework it has developed will likely influence physics for generations to come. As you drift towards sleep tonight, consider the space around you. It appears smooth and continuous. You can imagine dividing it into smaller and smaller pieces without limit. But if loop quantum gravity is right, this appearance is an illusion, an emergent phenomenon arising from a more fundamental discrete reality. At scales unimaginably smaller than atoms, smaller than protons, smaller than anything we can directly observe, space breaks down into quantized pieces, nodes and links carrying spins and intertwiners, the atoms of geometry from which the universe is built. This is a humbling and wondrous thought. The three-dimensional arena in which we live our lives, the stage on which all events occur, is not fundamental. It is emergent. It arises from something deeper, something stranger, something quantum. The fabric of space is woven from threads we are only beginning to understand. If you have enjoyed this exploration, please consider liking and subscribing to the channel. Your support allows us to continue bringing you these journeys to the frontiers of human knowledge. Leave a comment with your thoughts and questions. What aspects of loop quantum gravity do you find most intriguing or puzzling? What topics would you like us to explore in future episodes? Until next time, rest well. Let the mysteries of the quantum universe fill your dreams. And remember, the space that surrounds you, that you breathe and move through, might be far stranger and more beautiful than it appears. Good night. Appendix: the mathematics behind the mystery. For those of you still awake, curious to understand more of the mathematical machinery underlying loop quantum gravity, let us delve a little deeper into the structures we have discussed. This section is more technical than what came before, but the mathematics reveals patterns of extraordinary beauty. The starting point for loop quantum gravity is the reformulation of general relativity by Abhay Ashtekar in 1986. In the standard approach, general relativity is written in terms of the metric tensor, a mathematical object that encodes distances and angles at each point in spacetime. The Ashtekar reformulation uses instead a connection and a frame field, objects more familiar from gauge theories, like electromagnetism and the nuclear forces. A connection describes how to parallel transport objects along curves. Imagine walking around a curved surface like the Earth while keeping an arrow pointing north. The direction north changes as you move, and the connection keeps track of this change. In Ashtekar's formulation, spacetime has a connection valued in the Lie algebra of the group SU2, the same group that describes the spin of electrons and other fermions. The frame field, also called a triad or Vierbein, depending on dimension, specifies a set of orthonormal directions at each point. You can think of it as a tiny coordinate system attached to each point of space. The frame field is related to the metric, the mathematical object encoding distance, but it carries additional information about orientation. The remarkable fact is that general relativity, written in terms of these variables, looks very similar to Yang-Mills theory, the theory of the strong and weak nuclear forces. The constraint equations take a simpler form. The phase space has a cleaner structure. This similarity suggested that techniques successful in Yang-Mills theory might be applicable to gravity. The key variables in the quantum theory are holonomies and fluxes. A holonomy is the parallel transport of a spin along a curve. If you move around a closed loop and return to your starting point, you generally find that a vector has been rotated by some amount. This rotation is the holonomy of the loop. In the quantum theory, holonomies become operators that act on quantum states. Fluxes are the variables conjugate to holonomies, analogous to momenta being conjugate to positions in ordinary mechanics. They measure the gravitational flux through surfaces, related to the densitized triad. In the quantum theory, fluxes also become operators, and the commutation relations between holonomies and fluxes encode the fundamental quantum properties of spacetime. The Hilbert space of quantum states is constructed from functions of holonomies. A spin network state is a special function that depends on the holonomies along a graph embedded in space. The graph consists of edges and vertices. Each edge carries a representation of SU2, labeled by a half-integer spin. Each vertex carries an intertwiner, a mathematical object that couples the representations meeting at that vertex according to the rules of angular momentum. The inner product on this Hilbert space is defined using a measure on the space of connections, the Ashtekar-Lewandowski measure. This measure is uniquely determined by requirements of diffeomorphism invariance and cylindrical consistency. Its existence and uniqueness is a non-trivial mathematical result, established through work by Ashtekar, Isham, Lewandowski, and others. The area operator is constructed from the flux variables. For a surface embedded in space, the area is a functional of the triad field. Promoting this functional to an operator and computing its spectrum yields the famous result. Area is quantized, with eigenvalues proportional to the square root of j times j plus 1 for spin j contributions. The volume operator is more complicated. It involves the determinant of the triad, which becomes a complicated combination of flux operators in the quantum theory. The spectrum of the volume operator has been computed explicitly for vertices of various valences, revealing rich structure including a volume gap, a smallest non-zero eigenvalue. The dynamics of loop quantum gravity are encoded in constraint operators. There are three types: the Gauss constraint, which generates gauge transformations, the diffeomorphism constraint, which generates spatial diffeomorphisms, and the Hamiltonian constraint, which generates time evolution. Solving these constraints at the quantum level is the main technical challenge of the theory. The Gauss constraint is the easiest to solve. It requires that spin network states be gauge invariant, meaning that the intertwiners at each vertex must properly couple the spins of the edges meeting there. This is precisely the condition that defines spin networks, so the Gauss constraint is automatically satisfied. The diffeomorphism constraint is solved by considering equivalence classes of spin networks under spatial diffeomorphisms. Two spin networks that can be smoothly deformed into each other represent the same physical state. The space of such equivalence classes is called the kinematical Hilbert space modulo diffeomorphisms, or the space of S-naughts. The Hamiltonian constraint is the hard one. Thomas Tiemann constructed a well-defined Hamiltonian constraint operator in the 1990s, but its physical interpretation and the space of solutions remain subjects of active research. The constraint is written in terms of holonomies and fluxes, regularized in a specific way to yield finite expressions. Its action on spin networks creates and annihilates edges and vertices, changing the topology of the graph. The spin foam approach provides an alternative perspective on the dynamics. Instead of solving constraint equations, we sum over histories, different spin foams connecting initial and final spin networks. Each spin foam contributes an amplitude, and the sum of amplitudes gives the transition probability. This path integral formulation is analogous to the Feynman path integral in quantum mechanics. The EPRL-FK model specifies the vertex amplitude, the weight assigned to each vertex in a spin foam. The amplitude involves 15J symbols, generalizations of the familiar 6J, and 3J symbols of angular momentum theory. These symbols encode how the representations labeling faces of the spin foam combine at vertices according to the rules of SU2 representation theory, with additional constraints ensuring the correct geometric interpretation. Computing spin foam amplitudes is computationally intensive, but significant progress has been made using both analytical and numerical methods. The large J limit, corresponding to nearly classical geometries, has been studied extensively. In this limit, the amplitude is dominated by spin foams corresponding to discrete Regge geometries, discretizations of classical spacetimes. This confirms that general relativity emerges from the quantum theory in the appropriate limit. Current research explores many directions: the coupling of matter fields to quantum gravity, the quantum structure of black hole horizons, the emergence of cosmological perturbations from quantum gravity, the connection to other approaches like causal dynamical triangulations and asymptotic safety, and the mathematical foundations of the theory, including the measure theory of spin foams and the algebra of quantum observables. The mathematics of loop quantum gravity is beautiful and deep, drawing on topology, representation theory, differential geometry, functional analysis, and combinatorics. It connects to pure mathematics through relations with knot invariants, topological quantum field theories, and the theory of operator algebras. Whether or not the physical theory turns out to be correct, the mathematical structures it has revealed are valuable contributions to human knowledge. A final thought on the nature of reality. As you rest now, consider this: the deepest investigations of physics lead not to simple answers, but to profound questions. What is space? What is time? What does it mean for something to exist? These are not just scientific questions, but philosophical ones, questions that humanity has pondered for millennia. Modern physics, including loop quantum gravity, continues this ancient inquiry with new tools and new perspectives. The image of space as a smooth continuum, so natural to our intuitions, may be as misleading as the ancient image of the Earth as flat. The flat Earth seems obvious at human scales, but investigation reveals the curvature hidden by our limited perspective. Similarly, the continuity of space may be an illusion created by our inability to perceive the Planck scale directly. If loop quantum gravity is right, then every point you see around you, every cubic centimeter of the room where you rest, is not really a point or a cubic centimeter at all. It is a vast collection of spin network nodes and links, perhaps 10 to the 100 of them in every cubic centimeter, combining and recombining in quantum superposition to create the appearance of continuous space. The smoothness is emergent, arising from structure far below the threshold of direct perception. This is a stunning thought. The universe is not what it appears to be. Beneath the surface of things, at scales beyond our direct reach, reality has a different character entirely. Continuous becomes discrete, smooth becomes grainy. The fixed stage becomes a dynamic actor. The background becomes the foreground, and yet life goes on. The emergent world we inhabit, the world of tables and chairs and stars and galaxies, operates according to laws we can understand and use. The quantum realm below does not disturb our daily lives, any more than the atomic structure of matter disturbs the solidity of the floor beneath us. We live in the emergent world, and it is real enough for all practical purposes. But knowing that there is something deeper, something stranger, something more fundamental beneath the appearances, changes how we think about existence. It humbles us, reminding us that our intuitions are limited, that reality may always have surprises in store. It inspires us, showing that human inquiry can reach beyond the immediately given to uncover hidden structure. And it connects us, linking the everyday to the cosmic, the ordinary to the extraordinary. Sleep well, knowing that you rest in a universe more wonderful than you imagined. Dream of spin networks and spin foams, of quanta of geometry, weaving the fabric of space, of bouncing universes and quantum black holes. Tomorrow, when you wake, the world will look the same, but perhaps you will see it differently, knowing what might lie beneath. Good night.